Hello everybody, good morning. Myself, Dr. Shubhankar Sen, an Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the fourth lecture of Module 6 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the concept of Thomas algorithm, that is also alternately known as the tridiagonal matrix algorithm. So Thomas algorithm is a direct matrix equation solver. The Thomas algorithm or tridiagonal matrix algorithm, briefly known as TDMA, is an efficient direct matrix equation solver. The TDMA solves AX equals to B system such that its operation count is of the order of n, where n is the size of a square matrix. By tridiagonal matrix, we indicate the square matrices having three diagonals. A matrix capital A, when it is tridiagonal, it has three diagonals. So size of the matrix is n by n. So one main diagonal, one super diagonal, and one sub diagonal. So the remaining terms are 0. So here we identify this as super diagonal. This is the main diagonal, and this is the sub diagonal. The main diagonal contains n terms. The super diagonal and sub diagonal contain n minus 1 terms. The tridiagonal matrix system, its bandwidth is 3. The bandwidth of a tridiagonal matrix is 3, and its half bandwidth is 1. Tridiagonal matrices are generally obtained in one-dimensional heat transfer and fluid flow problems when we use the Galerkin formulations. The tridiagonal matrices are characteristic to one-dimensional heat transfer and fluid flow problems using Galerkin finite element formulation with linear or two-noded bar elements. Now let us illustrate the algorithm for solving the degree of freedom from a tridiagonal matrix equation system. So let us consider a tridiagonal matrix equation system Ax equals to B, where A is known as the coefficient matrix, X is the degree of freedom or unknown vector, and B is the known load vector or the force vector. So let us consider A equals to D1, D2, D3 up to the last term Dn in an n by n matrix equation system. Then let us consider the superdiagonal terms as A1, A2, A3, An minus 1, remaining terms are 0 in the upper triangular portion, and the subdiagonal terms are B2, B3 up to Bn, and remaining terms are 0 in the lower triangular portion. So the diagonal terms D consists of n terms D1, D2, D3 up to Dn. The superdiagonal term consists of n minus 1 terms. They are A1, A2, A3 up to An minus 1, and the subdiagonal consists of n minus 1 terms B2, B3 up to Bn. The right hand side load vector contains n terms. These are C1, C2, C3 up to Cn. The degree of freedom or unknown vector contains n terms T1, T2 up to Tn. Therefore, this Ax equals to B system is given as this is the coefficient matrix A. Here we consider the unknown as temperature. This is T1, T2, Tn minus 1 to Tn. So square matrix is of size n by n. The degree of freedom vector is of size n by 1, and the load vector is of size n by 1 with entries C1, C2, Cn minus 1, Cn for n by 1. In the first row, we have D1, A1, remaining terms all 0. In the second row, we have B2, D2, A2. In the n minus 1th row, we have A n minus 1, D n minus 1, B n minus 1. In the nth row we have Dn and Bn. So remaining terms in the matrix, they are all zeros. So this is the tridiagonal matrix, capital A. This is the load vector B, and this is the degree of freedom vector. We have denoted it by symbol small x. Now, this Thomas algorithm, this is a special case of Gauss elimination method. The TDMA is a special case of Gauss elimination. The fundamental steps in TDMA are: number one is the forward reduction, and number two is the back substitution. Both of these steps are fundamental steps in the Gauss elimination method. Now, to illustrate the algorithm of Thomas algorithm, let us consider n equals to 4. Let us consider n equals to 4 for illustration of the Thomas algorithm. So we have the matrix Ax equals to B. This is given as D1 A1 0 0, B2 D2 A2 0 0, B3 D3 A3 0 0, B4 D4. So we have a 4 by 4 square matrix. This is A, and the degrees of freedom, they are T1, T2, T3 and T4. Our known RHS vector is C1, C2, C3 and C4. So in Thomas algorithm, we keep the first row as unchanged during the operation, and also the super diagonal terms are not changed. So the key steps involve retain the first row in its original form, and the same thing will be done for the super diagonal. Also preserve the super diagonal terms. The meaning is that these terms are not altered during the TDMA calculations. So after we perform the forward reduction, the matrix will have the following form. After forward reduction, the Ax equals to B matrix assumes the following form. our first row, it does not change. So D1, A1, they remain as they are. So here we have T1, T2, T3, T4. Since the first equation does not change, the right hand side of the first equation, that is given by C1, it also does not change. Then we go for the next step. In the next step, B2, B3 and B4, they are all made 0. It means that the matrix, it becomes an upper bidiagonal form, or the subdiagonal is eliminated. So here we have 0. Then D2 becomes D2 dash, A2 remains as it is, A2, and then the 0 is there. In the third row, we have again 0 at the place of B3. D3 becomes D3 dash, and A3 retain its original value. At the last row, we have B4 equals to 0, and D4 becomes D4 dash. So in the right hand side, C2 becomes C2 dash, C3 becomes C3 dash, and C4 becomes C4 dash. So the first row remains unchanged. The forward reduction renders B2 dash equals to 0, B3 dash equals to 0, and B4 dash equals to 0 after row reduction or forward reduction. We get an upper bidiagonal matrix. So our new matrix equation system becomes A dash x equals to B dash. So this is our A dash matrix, and this is our B dash matrix. So the tridiagonal matrix is converted to an upper bidiagonal matrix by the forward reduction or the row reduction operations. It means that the subdiagonal terms B2, B3 and B4, they are eliminated during the elementary row operations. So this leads to the change of the diagonal terms from the second row or the second equation to the last row and last equation, and this is reflected also in the right hand side variable. So all the C values, they change from C2 up to Cn. These terms become C2 dash, C3 dash up to Cn dash. Now let us go back to the original equation. Consider the original matrix. Here we had D1, A1, 0, 0, B2, D2, A2, 0, 0, B3, D3, A3, 0, 0, B4, D4, T1, T2, T3, T4. This is C1, C2, C3, C4. Now let us consider the first two equations. The first equation is D1 T1 plus A1 T2 equals to C1. The second equation is B2 T1 plus d2 t2 plus a2 t3 equals to c2. Now from these two equations we have to eliminate the coefficient b2. So we have to eliminate b2 from equation 2. The new equation 2 can be obtained as multiply equation 2 with d1 and subtract from it equation 1 multiplied with b2. So this gives us equation 2 into d1. This gives us b2 d1 t1 plus d1 d2 t2 plus a2 d1 t3 equals to c2 d1. And now the first equation multiplied with b2, it gives us b2 d1 t1 plus a1 b2 t2 equals to c1 b2. Now we perform the subtraction. This subtraction eliminates the coefficient b2 and then we are left with d1 d2 minus a1 b2 into t2 plus a2 d1 into t3 equals to c2 d1 minus c1 b2. Now in the converted equation or in the final equation after the forward reduction, the second equation, its appearance is given as d2 dash t2 plus a2 t3 equals to c2 dash, because the matrix has this following form after the row reduction. So d1 a1 0 0 0 d2 dash a2 0 0 0 d3 dash a3 0 0 0 d4 dash multiplied with t1 t2 t3 t4, it gives us c1 c2 c3 dash c2 dash and c4 dash. In this upgraded equation, row reduced upper triangular or upper bidiagonal matrix, it gives us d2 dash t2 plus a2 t3 equals to c2 dash. So it means that this portion, this term a2 d1 t3, it should look like a2 t3. Since our desired equation is d2 dash t2 plus a2 t3 equals to c2 dash, the above equation we mark as equation 3. Equation 3 is simplified further by dividing its both sides by d1. This gives us d2 minus a1 into b2 by d2 into T2 plus A2 T3 equals to C2 minus C1 into B2 by D2. So the first coefficient of T2, this is equivalent to D2 dash. We got the desired form A2 T3, desired term is matching. In the right hand side we are getting C2 dash. So this gives us D2 dash equals to G2 minus B2 this is D1 and this is D1. So D2 minus B2 into A1 by D1 and C2 dash equals to C2 minus B2 into C1 by D1. So we got one recurrence relationship which can be used for conversion of the other diagonal terms and the right hand side vector terms. So this gives us by mathematical induction D3 dash equals to D2 dash minus B2 into A1 by D2 dash and C3 dash equals to C3 minus B2 into C2 dash divided by D2 dash. Here C2 dash equals to C2 minus B2 into C1 by D1. Here this B2 into C1 by D1 acts as the correction term and C2 is the original term. In the same way, D2 dash equals to D2 plus correction equals to D2 minus B2 into A1 by D1. So now we can generalize this upgraded diagonal and the right hand side entries. Here this is D3. Similarly this is B3. This is A2 and this is B3. So this expression we can write once more as C3 minus B3 into C2 dash by D2 dash. We can generalize the modified diagonal and RHS terms as di equals to di minus bi into ai by d dash I minus 1 and ci equals to ci minus bi into c dash I minus 1 by d dash I minus 1. So this is a minus 1 where I is varying from 2 to n because we do not change the first equation. Now after elementary row operations we get an upper triangular matrix. So after forward reduction the matrix equation system in upper bidiagonal form looks like D1 A1 0 0 0 D2 dash A2 0 0 0 D3 dash A3 0 0 0 D4 dash T1 T2 T3 T4 equals to C1 C2 dash C3 dash C4 dash. So here we can perform the back substitution starting from the fourth or the last equation, and then we can calculate T1, T2, T3 and T4. Starting from T4 we can move upwards. Perform back substitution. The fourth equation gives the last or fourth equation gives D4 dash T4 equals to C4 dash. This gives T4 equals to C4 dash by D4 dash, and the third equation gives the third equation gives D3 dash T3 plus A3 T4 equals to C3 dash. We already know the value of T4 just in the above step. So in this equation, T3 is the unknown quantity. So this is known. So T3 is unknown. So this gives us T3 equals to C3 dash minus A3 T4 divided by D3 dash. So now we can generalize the back substitution formula. The back substitution formula is generalized as Ti equals to C dash I minus Ai T I plus 1 by Di dash. For I, it is varying from n minus 1 to 1 in steps of minus 1, and Tn equals to Cn dash divided by Dn dash. Now combining forward reduction and back substitution, the TDMA pseudocode may be given as here. This is Di dash. This represents updated value of Di, and this left hand side portion is Ci dash. So these two statements, these are equivalent to assignment statements. It means that the value of Di, it is updated and then assigned to itself, and we get a new updated value. Same holds for Ci also. Ci becomes Ci dash. Do I equals to 2 to n Di equals to Di minus Bi into ai minus 1 by d I minus 1, ci equals to ci minus bi into ci minus 1 by d I minus 1 and do. So this is the forward reduction step. So this is bi and the back substitution is Tn equals to Cn by Dn, do I equals to n minus 1 to 1 in steps of minus 1, Ti equals to Ci minus Ai T I plus 1 divided by Di and do. So this is the pseudo code for the Thomas algorithm for solving the degrees of freedom in a tridiagonal matrix that is generally obtained in the one-dimensional heat conduction and fluid flow problems. Now we shall illustrate the implementation of Thomas algorithm for the heat conduction problems that we have already solved by using finite difference, finite volume and finite element method. Illustration of TDMA for 1D heat conduction. So problem 1. So we have one 1D rod. It is of 1 meter length. It has 100 degrees centigrade at the left boundary and 50 degrees centigrade at the right boundary. So left boundary is x equals to 0. The right boundary is x equals to 1. This is the x-axis. So we have thermal conductivity K equals to 1 watt per meter degree centigrade and rate of heat generation is 1 watt per meter cube. Our governing equation is K del square T plus Q equals to 0 in one dimension. So we have already solved this problem and then we can show the matrix directly. So discretize the domain using 6 nodes so that delta x equals to 0.5. So we have 6 nodes. So this is delta x equals to 0.2. So this is unknown temperature T1, unknown T2, unknown T3, unknown T4. The known left hand boundary temperature is 100 degrees centigrade and right hand side boundary temperature is 50 degrees centigrade. So temperature is our degree of freedom T1, T2, T3, T4. We have to find it. Here this is an error in writing. The mesh size is 0.2. So this Di, this is Di nu and Ci in the left hand side is also Ci nu. So Di nu, it is equivalent to Di dash and Ci nu equals to Ci dash or the updated value. Now the matrix equation system, the tridiagonal matrix equation system is given by -2, 1, 0, 0, 1, -2, 1, 0, 0, 1, -2, 1, 0, 0, 1, -2. Here we have T1, T2, T3, T4. The known load vector is -100.04, -0.04, -0.04, and -50.04. So we have the variables in the variable form as D1, A1, 0, 0, B2, D2, A2, 0, 0, B3, D3, A3, 0, 0, B4, D4. Then we have T1, T2, T3, T4. In the right hand side we have C1, C2, C3 and C4. So the data that we have, we can write D1 equals to -2, D2 equals to -2, D3 equals to -2, D4 equals to -2. Then we have A1 equals to A2 equals to A3 equals to 1. We have B2 equals to B3 equals to B4 equals to 1. We have C1 equals to -100.04, C2 equals to -0.04, C3 equals to -0.04, and C4 is -50.04. Now we use the transformation relations. So we know that D2 dash equals to D2 minus B2 into A1 by D1. So D2 dash will be D2, our D2 is -2 minus our B2 is 1, A1, this is also 1, divided by D1, D1 is also -2, so this is -2 plus half equals to -3/2. Then we have D3 dash. D3 dash is D3 minus B3 into A2 by D2 dash. Our D3 is also -2 minus B3 is 1, A2 is also 1, and we got D2 dash just now, that is -3/2. So this is -2 plus 2/3. This is -4/3. Then we have D4 dash equals to D4 minus B4 into A3 by D3 dash. So D4, this is -2 minus B4 is also 1, 1 into A3 is 1 divided by D3 dash that we calculated just now. So -4/3 equals to -2 plus 3/4 equals to -5/4. So we have calculated the updated diagonal terms. Similarly, we can calculate the updated right hand side load vector. So C2 dash equals to C2 minus B2 into C1 by D1. Our C2 is -0.04 minus B2 is 1 into C1. C1 is 100.04. At the bottom we have D1. So D1 is minus 2. So this gives us minus 0.04 minus 50.02. So this gives us minus 50.06. Next we have C3 dash. C3 dash equals to C3 minus B2 into C2 dash divided by D2 dash. Our C3 is also minus 0.04. Our B2 is 1. C2 dash we have calculated just now. This is minus 50.06, and D2 dash we got it as minus 3 by 2. So minus 3 by 2. So this is minus 0.04 minus 50.06 into 2 divided by 3. So this comes as minus 0.04 minus 100.12 divided by 3. We get it as minus 0.04 minus 33.3. Roughly we can take it as minus 33.37. So here we get it as minus 33.41 roughly. Then we have the last term C4 dash. C4 dash equals to C4 minus B3 into C3 dash by D3 dash. Our C4 is minus 50.04 minus 50.04 minus B3 is 1 into C3 dash. C3 dash is minus 33.41 minus 33.41 divided by D3 dash, and D3 dash is minus 4 by 3. So this is minus 4 by 3. So this is minus 50.04 minus 33.41 into 3 divided by 4 minus 50.04 minus 100.12 divided by 4 equals to minus 50.04 minus 25.03 equals to minus 75.07. So we have calculated all the updated terms along the diagonal matrix as well as the right hand side vector. So we can substitute these terms in the updated matrix. So in this expression, this will be B3 and here it is B4. So this portion, this is 100.23. So this 100.23, if we divide by 4, we get roughly 25.06. So we update the value, and then so this is minus 75.10. The final matrix equation system after forward reduction is given by Ax equals to B. Here we get our A is the first row is minus 2100, minus 2100. Then our first column remaining terms, they are all 0. Then our d2 dash, it is minus 3 by 2. So this is minus 3 by 2. Our upper diagonal term is 1, the super diagonal term. So the next row, the third row here, our b was 0 and our d3 dash, it was minus 4 by 3. The corresponding super diagonal term is 1. And finally our d4 dash, it was minus 5 by 4. Minus 5 by 4 into T1, T2, T3, T4. Our updated load vector data, they are given as C1 is minus 100.04. This is the original data, 100.04. Our C2 is now C2 dash, it is minus 50.06, minus 50.06. Our C3 has become C3 dash, it is minus 33.41, minus 33.41. And finally our C4 dash is minus 75.10, minus 75.10. Now with this matrix equation system available, we can perform the back substitution. Now we can perform back substitution to find T4, T3, T2 and T1. So the last equation, it gives us minus 5 by 4 T4 equals to minus 75.10 from the last row. We have one equation and one unknown. From here we can find out T4 equals to 75.10 into 4 divided by 5. So this is 15.02 into 4 equals to 60.08. Now from here we can calculate the T3 value. So we get the third equation as minus 4 by 3 into T3 plus T4 equals to minus 33.41. This gives us minus 4 by 3 T3 equals to minus 33.41 minus T4 equals to minus 33.41 minus 60.08. And then from here we get T3 equals to, this is 93.49, 93.49 into 3 divided by 4. Similarly, we can find out T2 and T1. So this is from the third row. Similarly, we can calculate T2 and T1. I conclude today's class here. We have shown the algorithm for Thomas algorithm or TDMA. TDMA is widely used for matrix equation systems arising out of one-dimensional thermofluids problems. TDMA can be used for multidimensional problems as well. For today's lecture, I suggest the students to go through the CFD books, the books authored by Tanhill, Anderson, Fletcher, Patankar and J.D. Anderson. All of these classic textbooks, they have illustrated the implementation of the Thomas algorithm. Thank you very much for attending today's lecture.